It's the language of the universe.
But I don't understand it.
Hello, and welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you back to episode number 113, where today we have Dr. Don Feiger from the Center for Detectors on the podcast with us. So Don, welcome to the show.
Hey guys, good to meet you and good to see you again, Parker.
Yeah, it's great to have you on. So I attended one of your lectures about detectors. I found it super interesting, and so I thought, this would be a perfect thing to talk about, something that we've actually never spoken about on the podcast. So it was just a kind of a perfect place to talk about this in more detail.
And if I'm not
Super,
mistaken,
that's great.
And if I'm not mistaken, I think Parker, you're actually going into, well, not really detectors, but it's more or less like related to, or at least like having a good knowledge on detectors is quite valuable to, I think, what you're doing in your master's. So the fact that we've never spoken about this before, plus the fact that it's going to be quite relevant to you in the near future, I think this is going to be quite fun for you mainly. And I think everyone's curious not only on how detectors work, but also like just in general cameras. And I feel like they share very similar properties. So I'm excited to see where this conversation can go. So,
Right. So nowadays, everybody has a camera in their pocket, right? So it's something that kind of everybody can relate to, and probably something that most people haven't explicitly thought about. Like, how does this camera actually work? Maybe they had the thought, but never kind of delved deeper into the inner workings of it. So that'll be awesome. So
Yeah, I think in the class that I gave in the lecture, I was asking people and the students in the audience, how many of you have any PN junctions on you right now? And I think very few people raised their hands. I think one of the professors did. And I said that I had millions of PN junctions because they're the things in the pixels in your camera phone. So you all have lots of PN junctions, and that's the fundamental element of many kinds of detectors that primarily detect photons, but they can actually detect other things. So yeah, they're ubiquitous. They're all over the place. We all have them. We all have super powerful detectors in our hands every day, and we don't really know the details of it. If you ask someone to explain what's in these locations here, these circles, might be a fun experiment to do. Just randomly ask people on the bus what's in the circles on your phone, and try not to ask anyone who's really angry or something. Ask a friendly person,
right.
and see what they say, and they probably don't know.
Yeah, so maybe like a fundamental question here is, what is a PN junction?
Okay. So a PN junction is it's a name given to a kind of circuit element in electronics that describes when a p-type and n-type material are in close proximity and there's a boundary between them. So that begs the question, what is a p-type and n-type material? It's usually referred to as a semiconductor that's been doped with some other element. So the semiconductor itself is made of one thing, and then there are other atoms or dopants interspersed into it, uh, giving it higher conductivity. And it's usually in a crystal structure, so it's a periodic structure where the atoms are equally spaced, as opposed to being amorphous, where the atoms are sort of randomly spaced.
Mm-hmm.
And this crystal structure that's a semiconductor has the property that if a sufficiently energetic photon hits it, then the material can absorb the photon and an electron can be promoted from the valence band where it's stuck in the crystal structure into the conduction band where it's free to move around, perhaps in the presence of an electric field. And in a detector, uh, scientists and engineers use this property to detect light and then steer it into a little bucket, and that's the PN junction that can hold the charge. Uh, so the PN junction is the thing that holds the charge when you take a picture in every single pixel. So every pixel has one of those PN junctions in it. And at the end of the exposure, there's a little circuit connected so that there's a wire that goes to every single PN junction. So if you have a 16 megapixel detector, you have 16 million PN junctions, and then you have 16 million wires, each connected to a PN junction. And those are all connected to a multiplexing circuit that sends the voltage on the PN junction to some sort of analog to digital converter that converts the voltage into some digital number. And let's say it's 16 bits, so you have 0 to 65, 535 numbers possible in 16 bits. And then something like a computer monitor or your phone display can show you a representation of those values in a two-dimensional array that mimics the two dimensions of the detector. And we call that thing a picture.
Wow. So essentially, a PN junction is something that holds the electrons, and then,
Yeah.
or it holds the charge, and then the goal of, then afterwards, the goal is to just see how much charge has been collected at every single point, and then to convert that into a 2D image.
Yeah, yeah. So that conversion is called deinterlacing. So the way it usually works is I said there were 16 million pixels, 16 million PN junctions, 16 million wires. I didn't tell you there were 16 million A to D converters because there are not. And A to D
Hmm.
is a very complex thing, so you probably can guess what I'm going to say. The data are multiplexed into a smaller number of A to D converters, like 16 or 32 or 64. And so you can imagine a big switching circuit that connects pixels to these A to Ds. So they're
Hmm.
processed in parallel channels. And then at the very end, often, not always, but often, that output itself is serialized into one wire. So you can
Okay.
imagine to take a movie, you're taking 30 or 60 frames a second, 16 megapixels, 16 bits. Um, I can't calculate that fast enough, but if that has to go down one wire, it's maybe gigabit or something. So all that's happening in your phone, which
Wow.
which
Does
to
it?
me is remarkable.
Right. I was wondering in the does this have any or I mean does this rely on the principle of the photoelectric effect, or are they
Some people use that term, but I don't.
right?
I don't because the photoelectric effect, at least the way I learned it, was in the context of things like photomultiplier tubes, where the photon actually liberates an electron from the material,
Right. Is that
and the energy it has to have is called the work function.
Hmm.
Um, so here I'm not talking about the electron leaving the detector; it's just elevating it to the conduction band.
so? My understanding, or again, correct me if I'm wrong, but like my understanding of photoelectric effect and where it applies is mainly solar panels. Is what I usually tell people when they're like, "Oh, why did he
Oh
get the
yeah,
Nobel Prize?" So
yeah,
by that same logic, I would think that that electron is being then conducted via
yeah.
after
It's
being hit
it's the
by a
same exact
photon.
thing as a photovoltaic cell,
Okay.
except there um, there's usually a current that flows, uh,
Okay.
and here the detector is operated in open circuit. Um, there isn't the energy generation property in the detector that there is in the photovoltaic
Hmm.
cell. Um, I
Right.
don't know if you guys,
Right.
yeah, yeah,
So
go ahead, yeah,
no, I
yeah,
was I
it's
was
a
just
similar
wondering.
property.
Right. So it's a similar property. But then how does the electron get conducted if there's nothing running through the circuit?
So
Like how does it get
in,
stored at some place if there isn't like some potential difference, or am I
sure,
understanding the diagram
yeah, yeah.
incorrectly?
So I think it's fun to talk about this. It's a little bit more detailed,
Right.
and
Hmm.
I left
Hmm.
that out. But let's just go back to the PN junction.
Hmm.
So the P type dopant. So I said that the semiconductor is doped such that there's a part that's P type and a part that's N type. So
Right.
let's take silicon for example, which is a type 4 material in the periodic table, and that means there are 4 electrons in the outer shell. And if you take silicon and form a crystal, then the neighboring silicon atoms will share an electron in a covalent bond. And so you can imagine an silicon atom surrounded on all 4 sides by
Mm-hmm.
neighbors, and they're all in covalent bonds. So those 4 electrons are all locked up
Mm-hmm.
in covalent bonds. But imagine you add something like a boron, which has 3 electrons in the outer band. And if the boron atom is sitting in the crystal in the place where normally there would be a silicon atom, let's say,
Mm-hmm.
and now there's one open space that's not being occupied
Right.
because there's not a covalent bond. So that becomes a p-type. Now that's not to say that the material has become positively charged, not at all, because the boron only has 3 electrons, uh, but it has only 3. Well, it's a
But
matching number of protons. I can't remember boron how many protons it has, but the total number of electrons it has is equal to the total number of protons it has. So it's neutral. So the material is not positively charged. It just has a positive acceptor or receptor.
mm,
Mm.
And then the N type is going to be a material that's type 5, let's say, that has 5 electrons. And now what happens is there's an extra electron that's not in a covalent bond with the silicon neighbor.
right.
So now you have a weakly bound electron on one side, the N side, and then you have excess holes on the P side.
Mm. So it's like
And
there's a giver and a receiver.
yeah, yeah, a donor and receptor, you could call it.
Oh, there you go.
Yeah, and then what what happens naturally, due to local fields, is the electrons can migrate from the N type to the P type.
They
Right.
they can. Sorry, you said can.
They
That's
they,
how
they
they.
can. Yeah, those
Right.
loosely bound electrons can fall in the holes on the other side of the,
Right.
the border. Okay? And
Oh.
imagine this happens a lot.
Mm-hmm.
And what's happening is the P side actually is getting a net negative charge. That is a net negative charge because there's
Hmm.
too many electrons
'Cause it's
for the
going.
number of
Okay.
protons.
Right.
But when they leave a hole.
Hmm.
And when they leave a hole, that uh, means that the negative charge that made it neutral before is no longer there. And so it's a net positive charge. Okay, so now we have a
Mm-hmm.
region where the electrons migrated over, establishing a negative charge, leaving behind it something that is now positively charged,
Mm-hmm.
which might remind you of a capacitor, a charged capacitor.
Right.
And it might also inspire you to think about electric field vectors. So now there's an electric field pointing, according to convention, pointing away from the positive side to the negative side. But oddly enough, that means away from the N type to the P type.
Right.
Mm-hmm.
Right.
Okay, now there's a point you can imagine where if any unruly electrons try to jump across the border, at some point that electric field that's been established is going to push it back.
Mm-hmm.
Hmm.
So there's a
Sure.
point where this stops. And when it stops, we would say that the space charge is what it's called in that region at the border of the PN junction has stabilized, and that the charge difference is established by these migrating charges that are now stuck in the crystal lattice. They're not freely moving around, they're stuck in the crystal lattice. And because of this, that region is called the depletion region. It's depleted of any free charge.
Mm.
Okay.
Okay, now imagine we've just been talking about the PN junction, right? So imagine a photon comes in and strikes the bulk of the material that extends beyond the PN junction, and it liberates an electron which floats towards this PN junction, let's say. And let's say it falls into one of the holes on the N type that was left by one of the electrons that migrated. Well, the electric field vector will become 1 unit of charge weaker.
Mm-hmm.
And then guess what? One of the electrons can now drift over to the other side.
Oh, okay. So by adding new electrons, it's kind of shifting over this region.
Well, no. So what it does is it momentarily makes the depletion region smaller. When I say momentarily, I mean like picoseconds or something.
Okay.
And then it bounces right back to where it was. Nothing has happened. Okay, because the charge went there. It made that intrinsic electric field a little bit weaker, meaning that a rogue electron can now drift over because it's not being resisted by the
Mm,
full electric field. And then boom, the electric field goes back. So you've made a bad detector at this point. Just at this point, you've
right.
made a bad
Okay.
detector. Okay.
Because right now you can't detect anything because it just stabilizes immediately back to the same place that it was a picosecond ago.
Yeah. So one of the words we use is integrate. It's not a good integrator. It
Mm,
doesn't take good integrations.
Mm.
Okay. So what we need to do is connect that PN junction to a voltage source, say a battery, to apply an external electric field to bias it to make the electric field uh, bigger, so the depletion width gets wider. And
Right.
we do this by reverse biasing it. Okay, and so we set the voltage in order to apply this field, and now the depletion width is wider. And then we do something very important. We open the circuit, we disconnect the battery or disconnect the voltage source. Now the depletion width is wider and it can't collapse down because there's no circuit to deliver charge around the circuit to the other side, which is the way it would
mm,
go back to the intrinsic width. So now we've created a well, a quantum well or a bucket, um, which can then collect charge. Now what happens next is now we expose it to light again, and electron hole pair is created. They drift towards this depletion region. They fall into a hole, uh, and the total voltage across that depletion width goes down by a little bit, and then it stays perfectly still. And then another photo-generated electron hole pair comes in, and it goes down, down, down. The place where it can't go any further is the intrinsic depletion width, because whenever you try to shrink that down, it's going to bounce right back by
Bounce
the
right back.
rogue
mm-hmm.
electrons that just drift over to the other side. So you had to reverse bias this
Mm.
Mm-hmm.
Mm.
in order to establish the place where the charge is integrated.
So when the depletion region goes down to its original width, is that kind of the saturation level of the image where you
Yeah,
can't really collect more
yeah,
electrons, essentially?
right. Yeah, that's called the well size,
Mm.
usually expressed in the number of electrons.
Oh, cool. So yeah, just for the viewers, the listeners out there, when something is when we say something is saturated, it essentially means that you reach a level at which everything kind of has everything reaches one value, and you can't really detect anything beyond there. So in practical terms, when you turn on a bright light in your room and you take a picture of it with your camera, the one spot of the light just looks completely white. And why? Because there are so many photons coming in that your detector kind of reaches that upper limit and just says, you know what, this has reached the saturation limit where nothing else can be detected. So yeah, a little bit of context.
You know, in the
So
old
thank you to Brilliant for sponsoring this episode of the Math and Physics podcast. If you've been listening so far, and well, hopefully you've been enjoying it, then you should know that Brilliant has a lot of these things that we've actually been talking about so far in the episode: astrophysics, data processing, signal processing, and multiple other courses on their website that you can go check out at the link in the description below, or brilliant.org/MPP. The first 200 people to click that link actually get a 20% discount off of your premium subscription. So who knows? Maybe click that link and all of a sudden you know everything. No. Well, thank you to Brilliant for sponsoring this episode, and hope you enjoy the rest of the show.
days, we
Sorry.
used to have this stuff called film. Do you remember that? It was like in these little
Mm-hmm.
canisters, and you'd stick it
Yeah.
in your camera, and you'd take these pictures. Who knows if they were good pictures? Then you'd send them to some magic place, and then
Yeah.
later you'd have to go pick them up, and they're all saturated or overexposed or.
I actually have a film camera.
Oh, is that right? Is it?
Yeah,
It's kind of like a retro cool thing, right?
yeah, yeah, yeah.
Yeah, yeah,
It's
yeah. I understand someone still processes film. I don't know.
yeah.
And it
Well,
does that work in is that just using what the basically doing what the the AD converter does, but just post?
Uh, so that
Is that what
so
that's going on there?
with film,
Yeah, yeah.
yeah. So with film, it's a silver halide crystals that react and change the transmissiveness of the film in proportion to how much light hits it.
hmm.
So
Oh,
that's a
okay.
photochemical response, which sounds like alchemy. That sounds crazy, but I guess someone, um, I don't remember who figured that out, but you can imagine when people were doing crazy things, combining things together to see what would happen. Someone figured out if you expose this material, this emulsion, to
Hmm.
Hmm.
light, then it the silver halide is photoreactive. And I think when film is developed, um, some of the material washes off, and then that changes the transmissiveness of the film, and that results in the negative. And then you take the negative and project light through it, and that ends up making a positive print on photosensitive paper.
Oh, so the
What
detecting
about?
part
Oh,
is kind of the reverse of the imaging part, and then you have to you have to
Yeah,
invert the process to get the original image back.
yeah, yeah. And I don't know what material is in the photographic paper. Well, like I said, the silver halide was in the other one, but maybe it's the same. I don't know.
what about images with color? I would think that. I mean, my assumption is. I mean, correct me if I'm totally on the wrong track, but like, how have you been explaining it so far? Maybe like because I mean, color is just different energy light, so maybe it like releases. Oh, it can't be different energy. Okay, maybe just explain it because I don't really know where I was going with that. How would
Yeah, well,
in the same way you explain like the light getting brighter or darker?
right.
How would that interpret with color?
So I think it's interesting to just ask the question, how would you make a color um, detector? So I explained the PN junction and pixels, et cetera. And the way it's done usually is something that's kind of a brute force method. You put a tiny little square filter that only allows a certain color range
Mm.
or wavelength range to hit each pixel,
Okay.
and you put that on top of each pixel. Now that also sounds
Mm,
insane and crazy because pixels, like in your cell phone, are a micron by a micron or so. But there's a process of doing this, you know, just like there's a process for fabricating electronics. And usually there's a red filter on one pixel, and then on the pixel above it is a green, and then a pixel to the right of it is another green, and the pixel to the upper right of it is a blue. So you have
oh.
RGGB, and green gets two, and it so the detector is more sensitive in green. And then what you have to do is design an optical system that is blurry enough that objects fall on 4 pixels. So each point of the object falls on 4 pixels. Sort of the diffraction
Oh.
limit blurs across 4 pixels because it would be very disturbing if my ear was red and then my eye was blue and then my nose was green because those parts of my body were falling on the different pixels. So the answer is don't build that kind of optical system. Build the kind that is where the 4 pixels covers the smallest possible feature you could possibly detect.
Hmm.
Okay. And is
So
there like
in
a
this case,
mechanical? Oh, sorry. I was just asking if there's like a mechanical part that forces that to happen. Like, what if it isn't that
Oh,
situation,
so
or
the way to
is there
do
a
that
limit?
is you just design the optics so that it projects a diffraction limited spot onto 4 pixels. So consider that a point like object ends up not being a point due to the diffraction of an optical system. it ends up being a blur, right?
Mm-hmm.
Mm.
Mm-hmm.
And which is unfortunate, right? That means there's a fundamental limit to the resolution one can get when using an optical system.
Right. Exactly.
And so what happens is a point-like object, a dot, infinitesimal, so a true point, ends up getting imaged by an optical system, and it turns into something that kind of looks like a Gaussian distribution.
Mhm.
So it's kind of a normal distribution with a sort of a hump and the symmetric wings on either side of it. And ideally, you build the optics so that the full width at half maximum, so the width where it's half intensity, that
Mm-hmm.
width covers 2 pixels or 3 pixels.
Oh.
So,
Okay.
so the whole two-dimensional blur Gaussian would pretty much cover 4 pixels.
Mm-hmm.
So that way, um, you're getting all three colors on every single possible point in the image. And then when you digitize it, you need to tell the computer which pixels correspond to the greens and which pixels
Right.
correspond to the reds and the
Right.
blues. And then your computer has to decide how to use that information. Sometimes what computers do is, like with 8-bit color, it uses a 32-bit word, let's say, and that's 4 8-bit bytes. And the first 8-bit is red, the second 8-bit is green, and the third 8-bit is blue. So you're capturing 8 bits of information. And each of those bytes can be anywhere between 0 and 255 in value.
Right. Right.
And then the fourth byte can be used in all sorts of ways. Like I remember the old days, Apple they called it the alpha channel, and they would use it to encode various attributes,
Mm-hmm.
um, having to do with contrast or brightness, or I think they use the word luminance. I don't know. There's so many words that actually mean the same thing when you map topics into different fields. Uh, so that's how the color is done. There's another way to do color, which is more difficult, I guess, and that involves a property I haven't mentioned yet. But the photons penetrate into this material and they get absorbed. But I didn't tell you that longer wavelength photons penetrate more deeply, and
Right.
short wavelength photons end up getting absorbed near the surface. So you
Right.
could imagine cleverly locating multiple PN junctions within the vertical structure of the pixel so that the blue is absorbed by some PN junction near the top and the red in the bottom and the green in the middle. That's sophisticated, and people have done things like that. There was a camera company, I just can't remember, that actually built something like that. The problem is the brute force clunky glass filter method works, and it's
Right.
cheap and it's
Right.
easy,
Mm.
and you don't have to have a clever pixel design. It can be pretty stupid. Um, so that's the one that's preferred. Now there are some military applications where they do something like what I explained with the multiple PN junctions. What they do is they put two PN junctions in the material, and they use the detector as sort of a very quick discriminator. So they get a measurement at one wavelength, a measurement at another wavelength, and they very, very, very quickly, before they shoot something down, determine the temperature of the thing because they match the points to a black body curve,
Oh.
Oh.
right?
Oh.
So if they're looking at something, flying at it at thousands of miles an hour and it has a certain temperature, then they might guess that it's bad and then shoot
Right.
it.
Right.
Mm-hmm.
So those are
So that
Interesting.
those are two color military
Okay.
detectors.
so they're fitting a black body curve with just two data points.
Yeah, what could go wrong?
Yeah, exactly.
You
I
mentioned
guess
something.
yeah,
Sorry. Go ahead.
it can be done. I mean, I think you have to know which side of the curve you're on. I guess
Mm-hmm.
Yeah.
the Veen side or the Rayleigh Jeans tail.
Hmm.
You mentioned something earlier about pixel pattern, or sorry, like the PN, or like I guess like the color pattern. And when you were describing the red, green, and blue, you mentioned like, oh, the greens on the top right, top, and the upper left, and like, what does that mean? Like, are there is there like a certain pattern to placing these colored quote unquote pixels together to like
Yeah,
best fit that Gaussian?
it's just repeated. It's a repeated pattern. So the way I explained it, I explained the colors corresponding to 2 by 2 pixels, right? And
Right.
so pretend that that's just repeated across the 2000 by 2000 pixels or something, and it's sometimes called I think it's called a color grid array or a Bayer or Bayer pattern is what they call it.
Okay.
Mm.
Okay.
And I I, I imagine I mean I wasn't involved in that work. See, I don't want to use a detector like that. For
Mm,
precision measurements, like in astrophysics, you would never use this cheesy, clunky method, right? Because you're making precise measurements.
Mhm.
right.
Instead, you use a detector without this array of filters, and you're taking monochrome images. And in order to extract color information, you have a big filter that covers the whole detector and it emits light of a certain wavelength range. And you take an exposure of an object and then you stop and move that filter and put a different filter and you take another picture.
Okay.
Mhm.
So get individual, like
Yeah,
colored images,
yeah,
basically.
yeah, yeah. And then afterwards, you would have to use some piece of software like
Mm,
Photoshop and define RGB layers.
Mhm.
And
okay.
then you want to synchronize them by cross correlating the features to make sure that they're positioned in exactly the same way. In the old days, there's a picture that I made of something called the pistol star. I don't know if you've ever seen it, but it's very oddly colored. It looks striking,
Mm-hmm.
and it's very oddly colored. It's sort of red, purple, sort of reddish in a nebula, and then the stars are bluish, but it's some sort of pastel blue. And then there are a couple stars that themselves are reddish. And you could ask the question, how is that picture produced? You could ask this question about any picture in astrophysics, and
Right.
it's all the same. So I took multiple images of the object with the Hubble Space Telescope, and I then combined them in Photoshop, defining my own colors. And I don't remember if it was intentional or not, but there's something about those fake colors that looks really captivating. They're very strange. It's very strange. It almost looks
Mhm.
cartoonish. It almost looks Van Goghish,
So
Starry
when
Night.
you so when you say that I made my own colors or like I defined my own colors, how is that related to the like how are these colors like in these astrophysical images, like the James Webb famous images, for example, related to the actual nature of what you're seeing or like what's actually
Yeah,
out there?
so you have to ask the person who made the picture. So
Okay.
in the case of the picture I made, I did something slightly different than the RGB. Okay, because I was looking for something very specific. It turns out the nebula is composed of gas. So it's hydrogen and helium gas that's ionized. So imagine a plasma of electrons that are floating around and not bound to their atoms. But
Mm-hmm.
there's some probability called the recombination probability that an electron that's floating around will recombine and fall to be captured by a nearby atom. So let's say it's hydrogen. So the hydrogen is a bare proton when it's ionized, and its electron is off in this plasma. And if the electron zips by the proton, there's some finite probability that it'll recombine into the hydrogen, but you don't necessarily know, it's not obvious, that it's going to recombine to the ground level, the lowest energy level, the n equals 1 in the Bohr atom.
Mhm.
It could recombine to n equals 2, or 3, or 5, or 100, n equals 100. And when it recombines to a certain level, it'll emit a photon, and it'll then cascade down to further levels. It can't go any
Right.
further than n equals 1. That's the lowest energy.
Right.
But as it's cascading and recombining, every time it recombines from one level to another level, it emits a photon of a discrete energy that's equal to the difference in energy between the two levels. Makes sense, right?
Mm-hmm.
So the
Right.
photon loses energy, the electron loses energy, and it produces a photon with that same energy. So what
Mm-hmm.
I wanted to do was take a picture of that nebula of recombining electrons. And so I chose a filter centered at 1.87 microns, which is a wavelength that corresponds to the energy of an electron transitioning from n equal 4 to n equal 3. And that happens to be called, for historical reasons, passion alpha. Passion is not like Passion of the Gods. It's Paschen, passion.
Mm-hmm.
Um, and anything to the n equal 3 level is called the passion series. And so 4 to
Mm-hmm.
3, 5 to 3, 6 to 3, 7 to 3. The alpha comes from the fact that it's 4 to 3.
Right. So
And
we're more familiar with like the Lineman series or the Balmer series. So
sure.
this is just a different
Yeah. Yeah.
going to a different level essentially.
Yeah. So Lyman is to n equal 1, and then Balmer is to n equal 2, and then Passion is to n equal 3, and then bracket.
Cool.
And then I think Humphreys and Fund, or Fund and Humphreys, I can't remember, is the higher ones. Um, so if you're lucky, you get your name put on one of these energy levels, I guess. I don't know if they still do
Mm-hmm.
that, but so
So what is it about the Passion series that you
oh,
said I'm going to image these specific energy
right. So
levels?
let's think this through. Consider these electrons that get captured, and like I said, the initial state could be n equals 100. Who knows, right?
Mm-hmm.
Uh, Now, if it's at 100, it could go to 99, or it could go to 98, or it could go to 97. It has a lot of options, right? But if you're at n equals 2, how many options do you have?
Just one.
One. So these electrons that cascade down, you could see that they're going to produce more photons in the lower n numbers because there are fewer channels
Mm-hmm.
to cascade. They have to go through the low numbered ones. So I would prefer to look at who knows 2 to 1 Lyman. Okay, but that's at where is that 1200 angstroms, I think. That's a very short wavelength, right? That's UV,
Mm-hmm.
and there's too much dust between us and the center of the galaxy where the pistol star resides to see that.
Okay, so the absorption level is too high.
Yeah, so now I say, okay, fine. No n equals 1. Let's go to 2. Uh, so that's H alpha or Balmer alpha, and that's at, what is it, 6535 angstroms or so. So that's red, optical red. For every one of those, no, let me say it this way, this is better. For every trillion photons at the galactic center at that wavelength, only one will get to us.
Wow.
So the
Is that because of
absorption,
it being absorbed? Right.
it's still the absorption.
Right.
Mm-hmm.
Right. Right.
It's still not good enough.
Mm.
So we can't do n equals 2. So now let's do n equals 3. That's passion. So now we're going to get something that's bright because it's a low n number, but that's at 1.87 microns. And at 1.87 microns for every uh, 20 photons emitted, we get one from the galactic center.
Much better ratio.
Okay, that's much better.
Yeah,
much
it's a
much
lot
better.
better than a trillion to one. So
Right.
Mm-hmm.
Right.
so we're forced to use the infrared to look at the galactic center because of the absorption of dust along the line of sight. So I took an image in 1.87, got a picture, and then I took an image at a wavelength very close to that. I can't remember what it was. Uh, I'll say 1.9. So it's a wavelength right next to it. Now, the first image at 1.87 has all the Passion alpha photons.
Mm-hmm.
And then the image at 1.9 doesn't have any emission from Passion alpha, but it does have emission from stars because stars emit like a black body, whereas the nebula is emitting just emission lines corresponding to all these
Right.
electrons bouncing around. So
Mm-hmm.
one's called an emission line spectrum, the other one's called a continuum spectrum. So now I have these two images. And what I do is I take 1.87 minus 1.9, and I get a difference image where everything goes away. All the stars go away, but the nebula is sticking out.
Mm-hmm.
And it turns out there are a few stars that are emitting Paschen alpha in emission lines, so those stars stay in the image. And I colored that a red. And then I took the 1.9 that has all the stars in it, and I colored that this funny pastel baby blue. So now when you look at the image, you see this red nebula. You look real closely, you see a few red stars
Mm-hmm.
Mm.
because those are actually massive stars emitting Paschen alpha from their hot winds, where there's an electron plasma recombining.
Right.
Okay?
Okay.
And then you see these blue things, and those are all the other stars that have no particular line emission in Paschen alpha. And so when you ask the question, what do the colors of the picture mean scientifically? What's the physics? You have to ask the person who made it. Because what I just described has very little to do with the traditional RGB.
Mm-hmm.
Right. So it's all just relative, basically, based on why or what research you're conducting or what the purpose of the research goal is,
Yeah,
or what the
yeah,
goal of the research is.
right. If you've seen a picture of a colored picture of the quintuplet cluster, which I also was working on, that the pistol stars in the quintuplet cluster, or the Arches cluster, or any star cluster, let's say near the galactic center or in the infrared, one of the questions people always ask are those false colors? And the
Mm.
first thing that comes to mind is that that's kind of a false question in addition to
Mm-hmm.
false colors, because everything's false in some sense. I mean, your brain is mapping uh, a photochemical reaction in your retina into something that we call colors, but that's
Mm-hmm.
all fake. I mean, that's just invented by your brain. Any picture you look at is fake. It's constructed out of some filter array, or it's constructed out of monochrome images taken through filters and then remapped into something like Photoshop, and then your brain refakes the sensation that your retina feels looking at it, and so it's a
Mm-hmm.
nonstop, carnival of fakeness. Um, but we make sense of it because we're used to it. So when we see a banana that's yellow, we say, "Awesome, that seems right." If the
Mm-hmm.
banana's purple, we'd say, "That's strange, that's odd." Um, so when people say, "Is it false color?" what they really mean is that is the RGB of the picture I'm looking at equal to the RGB of my eyes?
Right.
Is it the
Mm-hmm.
same color range? Now, for an infrared picture, that can't be the case because your eyes
Right.
can't see infrared. So one has to make a judgment call. And what we do usually in astronomy is we take the longest wavelength image and we make it red,
Right.
and the shortest
Right.
wavelength and we make it blue, and the middle one green. And then there are cases like I just explained this crazy case with the pistol star where the specific physics I'm looking for suggested to me that I do what I did in creating this false color image.
Right.
How does
So.
this how does something like the Doppler effect affect your work, or like, I'm assuming because
Oh,
you were looking at is this cluster the center of our galaxy, or is this a galactic cluster, or is in somewhere else? Because I guess
so the
that will also
quintuplet
matter.
cluster is in the center, depending on what you mean by
Mm-hmm.
center.
Or
But it's
right.
not directly around the black hole, so it's about 30 parsecs away from the black
Okay.
hole, and most
Mm-hmm.
people would still call that the galactic center. And the Doppler effect is very useful because let's say that I look at the quintuplet cluster, I see a bunch of stars, but it turns out that's a very crowded place anyway in the galactic center, so lots of stars everywhere. But if I point at any particular star and someone asks me, is that actually a member of the quintuplet cluster, or is it just a star that's hanging around? its vicinity. Well, one of the things I can do is I can measure the velocity of the star through the Doppler effect, and then measure the velocity of other members, bona fide members of the cluster,
Right.
and see if they're moving with the same velocity. And if they're co-moving, then there's a high probability that it's part of the cluster. Now the next question you would have is how do you measure the Doppler shift? So think of the Paschen alpha line, 1.87 microns. I don't know the rest of the digits, but that wavelength will change depending on how fast the object is moving to you or away
Right.
from you, which is called the Doppler effect. So, I mean, if it were moving really fast, the line could be shifted out of the transmission bandwidth of the filter, and you wouldn't see the Paschen alpha.
Exactly.
So it
Right.
turns out that the motions that we expect are hundreds of kilometers per second, and that's far too low to shift out of the bandwidth of the filter. But what you could use is you could use a spectrograph that makes a spectrum, and now you would see these lines at different wavelengths, and then you can calibrate the spectrograph by using recombining gases in a gas cell that you put in front of the telescope or in front of the camera here on Earth. And you can go look up in a book the wavelengths corresponding to all those lines from your krypton or your neon or argon. These are all noble gases that we use uh, to do this. And you can calibrate which pixel corresponds to which wavelength when you take a spectrum. And then you can measure if the line is shifted with respect to where it should be if the object were at rest, and then relate that to the velocity. So the velocity as a fraction of the speed of light, v over c, is equal to delta lambda over lambda, where delta lambda is the shift of the wavelength. So the fractional wavelength shift is equal to the fractional velocity with respect to the speed of light.
Mm-hmm.
And so that's what I did.
Okay.
So, have you ever had to do an observation where you knew that the Doppler shift would shift the observed wavelength outside of your filter? So, you'd have to change your filter in order to actually observe the desired wavelength.
Have I? Probably not, because uh, I mostly only look at things in the galaxy, and the speeds aren't that high. But think about a clever experiment. Consider this. Imagine you wanted to look at something in the universe, let's say, and you know that the universe is expanding and even accelerating, and objects that are further away appear to be moving away at a higher velocity from us, thereby shifting their wavelength. It's a cosmological redshift due to the expansion of space in the universe. So it's not exactly the Doppler shift, but it has a similar effect. And so what you could do is you could make a spectrum, or not a spectrum, an imager, and then choose a filter. And the filter, let's say, would observe Paschen alpha, but shifted a lot to correspond to galaxies moving away at tens of thousands of kilometers per second, let's say. And
Mm-hmm.
that would correspond to a fixed distance from us.
Right. So, you can kind of observe a slice of the universe at some fixed distance, depending on which filter you stick in front of your detector.
Yeah, yeah, and JWST kind of did that. It uses the same principle, but let me explain it because it's different in practice. So imagine, instead of designing a filter with a certain wavelength to accommodate a shift in order to look at a certain time slice in the universe, imagine instead constructing a bunch of filters at different wavelengths next to each other, and then taking a picture of the universe through a slice of the universe, and maybe you get 1,000 galaxies. And then you can write custom software that will look at every galaxy and see where it's brightest, and then thereby try to relate that to spectral features. And now you have a way of doing photometric. It's called photo Z or photo Z measurements. You have a way of measuring z, which is the cosmological redshift or distance. You can measure that for every galaxy in the image. And in particular, the name of the method that we use is called dropout. So I don't know if you've heard of that, but it corresponds to the fact that there's a sharp edge in the spectrum of stars corresponding to the wavelength that is where an electron gets ionized from n equals 1, which is the 912 angstrom wavelength. That corresponds to 13.6 electron volts, which is a unit
Mm-hmm.
of energy. So there's a sharp edge right there where the flux below that wavelength goes down to 0, because any photon of higher energy on the way here will tend to get eaten up by a neutral hydrogen.
Mm.
So it's hard for photons that are more energetic to get through the universe because they'll get gobbled up by neutral hydrogen going through it. Um, so there's a sharp edge there. Otherwise, the energy of a star looks kind of like a black body, but it has little chunks taken out of it for absorption lines corresponding to different atoms. But then there's this huge chunk taken out of it at that 912
Mm-hmm.
angstrom. Well, imagine that 912 angstrom is shifted all the way to 1.3 microns, let's say. Then a filter at 1 micron is going to show nothing or a faint galaxy because it's sitting at that big chunk taken out. And then
Yeah.
all of a sudden in the neighboring filter, the galaxy is going to be there.
Mm-hmm.
And now you know why it's called dropout, the dropout method. So,
Yeah.
so if you read any of the early release JWST papers on uh, the early universe projects, you'll see people identifying these dropout galaxies, and they can then estimate a crude redshift. And if it looks like it's important for some reason, like one of the things people did was whenever you build a big telescope, uh, people tend to go out and just do the dumbest thing or the simplest thing that makes a discovery, like shooting fish in a barrel as soon as the barrel gets full of fish, right? So with
Mm-hmm.
JWST, all you had to do was point it and you would discover stuff. So one of the first things people did was just look for the longest wavelength dropout, which corresponds to the furthest away thing, the high Z,
Yeah.
and then they could say, oh look, we found a galaxy that is in existence very close to the time after the Big Bang.
Mm-hmm.
And if it's the one that's furthest away and closest to the time when the Big Bang happened, then they have a record. And they say, look, this is the highest Z galaxy. And
Mm-hmm.
so when they run this software to estimate the Z's for 1,000 galaxies and they see a few of them that have really long wavelength dropouts, then they get really excited because because then that's a test on how quickly galaxies can form after the Big Bang, and that's one of the things you'd want to know if you want to understand how the universe was constructed.
I actually, are you? I don't know if we're talking about the same thing, but I actually was just reading on a paper submitted by the Rochester Institute of Technology, where I believe you work, um, called. I don't know if this is the name of the paper, but it's "Brilliant Galaxies of the Early Universe," and it was submitted just September 15th. And I believe they used JWST to, I don't know about find, but maybe discover early galaxies that they had never basically discovered. So
Yep.
was this like a recent discovery that JWST kind of employed?
Yeah. So there was something called the early release program. I think it's either that or close to that. Which
Early release science, cosmic evolution,
yeah.
early release science,
So it's an
right?
ERS. Yeah. So what
Right.
that is NASA held a comp when you use a telescope, you have to propose to use it, and
Mm-hmm.
maybe if you're lucky, you'll get selected. And so NASA held an open competition, and people proposed to do early science with JWST, and often there are big teams of lots of people who propose. And the paper you're talking about was probably uh, done by one of those teams that they're like, Are there a lot of authors on it? Probably like 50 authors or something.
So, well, I mean, the main person named here is Jehan Gartel Tape,
Yeah,
associate professor in the School of Physics. I don't know if you know that
yeah.
person.
So she's one of the ones, and she's either PI or co-PI. I don't remember, but she's one of the ones who proposed with a team to
Hmm.
do those kinds of observations, and those early release meant that you couldn't um, keep the data from the public. Normally, there's a proprietary period where you get to work on the data. But I think the
Okay.
rule for the early release was it was either immediately public or had a very short proprietary period. I don't remember. But the key to that science was this fish in a bucket thing, where you're looking. One of the goals was just to look for galaxies as close to the Big Bang as possible. Um, so the first question is, are the galaxies there? Another question is, what do they
Right.
look like? Are they It's like if you didn't understand human reproduction or development, right? And you found one human, like the aliens come and they find one human, and it's a 70-year-old man with gray hair, and then the aliens say, "How did this happen? Did this human get produced all in one fell swoop with
Right.
the
There's a
gray
lot of missing
hair,
pieces.
or
Mm.
was it smaller and it got bigger? Maybe it was bigger and it shrunk." Like I think I'm shrinking. I think I'm getting to that age, starting to shrink. Uh, was it born whole? And then the aliens go look around and they find a baby. They say, "Holy cow!" So we have one baby, this thing, and then we have the old guy with the gray hair. I wonder if one turns into the other, or maybe these are two different animals. One's a baby
Mm.
animal, and one's an old man animal, and they're not the same thing. And so when you look at these galaxies, you ask the question: did they form all at once, into an adult, or was it a baby, a small galaxy? And maybe there are a bunch of baby galaxies around, and maybe they bumped into each other, and that's how they became a bigger galaxy. And I guess what they found was, well, the galaxies are there, that's for sure, and they're there sooner after the Big Bang than expected. And they also have shapes and structures which imply a certain amount of complexity that we didn't expect.
Mm.
So it's like they're more mature than we expected
Mm.
so soon after the Big
Okay.
Bang. And that's one of the papers the paper you're reading is one of them. There's probably been, I don't know, dozens of papers.
What about mistakes? Now let me read one part of like the summary of this paper that I'm reading over here, and it mentioned that the Sears team, I'll call it, where they found some galaxy of redshift 11.5, and there was another team in Scotland that found a nearby galaxy that had a redshift of 16, z equals 16. But then the Sears group found out that because of a coincidence, I'm just going to quote this summary here, and maybe you can further explain it. Because of a coincidence that mimics the colors of a high redshift galaxy, the other galaxy is not at a redshift of z equals 16, but a redshift of z equals 4.9. So I guess my
Right.
question is, how can you make mistakes in while observing these or at least such large redshift mistakes? Or
Yeah.
is it simply because of ineffective equipment? Is it because of ineffective analysis? And where can it go wrong, really?
Yes. So I've sort of given you the answer already, but it would be hard to recognize. Remember, I was talking about shooting down a missile.
Mm-hmm.
Use
Right, right.
use two data
The fast
points,
missile
and
temperature.
then you interpret it as black body radiation of a certain temperature. Okay.
Right.
And I don't know if your listeners know what a black body curve is, but it's a continuous distribution of wavelengths emitted by objects at wavelengths that tell you the temperature of the object. So my body is nearly 100 degrees Fahrenheit, and so the peak emission of my body would be around uh, 3 microns. Sorry, 30 microns or so, which is really a long wavelength. Okay, but if my body were hotter, say hot as a star, then it also would emit like a black body, but the peak would be at a different location. So for the sun,
Mm-hmm.
it's 5,800 Kelvin. So what that's 58 times hotter than my body, and so the wavelength of peak emission would be 58 times shorter wavelength, and that puts it in the optical.
Hmm.
And so its peak radiation's in the optical.
Right.
And we were using this property to see if a missile was hot or not, right? Because if
Mm-hmm.
you observe
Right.
2 points on this black body curve, you can figure out the temperature. But we talked about a different effect with galaxies that are far, far away, as they say, and at high Z, that the wavelength distribution changes because of the expansion of the universe, not because of temperature.
Right.
So you go look at something and you have to ask yourself, are you seeing these values because the black body curve has been redshifted, or are you seeing these colors because the black body temperature is cooler?
Mm.
Mm. Right.
Both of them shift the curve. And if you're only going to take a
Right.
few data points, like with the missile, I said two, because the detector was a two-color detector. For JWST, I told you there were a set of filters. So it was like five or
Right.
six. I can't remember that they used. But you can still make a mistake, right? If you just have those data points and you try to infer the redshift without taking account of the fact that the galaxy is full of cold dust that dominates the emission of the light,
Mm.
then you've attributed your measurements to one phenomenon incorrectly. And I believe in the case you're talking about, the intrinsic color of that galaxy was redder. I'd have to go back and look at it, but I thought that's what it amounted to. They didn't account for
Mm.
dust. But remember when I told you about this process, either from the missile or the Lyman continuum cutoff at 912, in any of these processes, you have to start out with an intrinsic concept of what the distribution is, right? When you make your
Mm-hmm.
measurements, you have to say, I think I know what the intrinsic emission is. I know there's a Lyman continuum cutoff at 912, so I'm going to interpret the data points knowing that, attributing a big drop to a redshifted feature from 912. But if the values are due to cold dust, then your prior or your intrinsic model needs to be the cold dust,
Right.
not the
Right.
912.
Right.
And that's where that
Yeah.
mistake was made. And you just demonstrated what I talked about before when I said you take an image, you're shooting fish in a barrel, and you make quick estimates of your photo Z's. Then you need to go back and take a spectrum with a huge telescope and a spectrograph. And I don't know if that's what they did in that case of the 4.9 or whatever it was. Um, but you take a spectrum and then you realize, oh, this isn't the 912 cutoff shifted. It's actually a less redshifted dusty galaxy.
Mm.
Okay.
I had a question about JWST, which is pretty, I guess, congruent to what we're talking about. But when you're making an observation of something that is super far away, and you're only getting right a very very small fraction of the photons that were emitted by the source, how can you discern the photons coming from the object that you're looking at versus all of the noise from all of the other objects that are closer to you in the line of sight?
So if there's a faraway object and there happens to be another object that appears to be sitting right on top of it, like exactly on top of it, like two stars, one far away, one nearby. Uh, what you could try to do, so what you're measuring there is the collective light from both.
Mm-hmm.
And what you could do is go back and take a spectrum and hopefully if they have different temperature, you'll see two black bodies on top of
Right.
each other or summed together. Or you could see, if they're traveling at different velocities, you could have one of them might have a set of absorption lines, and another has a set of absorption lines, and they're shifted with respect to each other. So you see double lines.
Mm.
And then you can say, aha, these are two stars on top of each other. That actually doesn't happen very often. Um, the time it does happen is when the two stars actually are binaries around each other. But then they're at the
Right.
same distance, and then you could hope to see a double line spectrum that keeps shifting back and forth as the two stars Doppler shift.
Mm.
Alternatively, you have the red, blue, red, blue, red, blue, and they keep going
Mm.
back and forth in a sine wave.
Right.
Now, your question about how do you see things that are far away, don't have many photons, and how do you see it above the noise? So that's something that we can calculate, we estimate, and we calculate the signal to noise ratio.
Mm.
And so you can imagine, yeah, just like film in the old days, we had these big TVs that were made out of tubes.
I still don't know how those things work.
um, there's a hot plate that is hot enough, that electrons get excited enough to pop off the plate, and then it gets steered by orthogonal magnetic fields in a raster pattern into the front of the tube, and it's called an electron ray tube, um, uh, cathode ray tube. Sorry.
Cathode ray. I was gonna
Yeah,
ask
yeah,
that.
yeah.
It's the
CRT.
same thing. Right. Right.
Yeah,
Right. Yeah.
yeah. Uh, so you remember those old TVs before we had nice HD pictures all the time?
Yes.
You would get the noise, right? The salt and pepper noise if there was no signal or something. And sometimes I guess if you had an antenna but it wasn't great, you might be able to see a signal, but it was kind of intermixed in the noise or something. You couldn't really discern it. So you'd
Mm-hmm.
want the values. Remember from the PN junctions, you want the values from the pixels on the object to be higher than the values from pixels that are just staring at blackness, nothing in space.
Mm-hmm.
And for various reasons, um, even if the pixel isn't looking at anything, it'll have some noise, some voltage noise attributed to it. So the detector itself produces noise. Or it could be a kind of noise which is more like what you were describing, where you have, you know, a million pixels, and it just so happens there are a million objects in the frame. And now it's just sort of a blur of light. And
Mm-hmm.
that has a name. It's called confusion limited. We're really good at making up names in astronomy.
Yeah.
So,
Okay.
so that's the confusion limited case. So in my thesis, I did my thesis on the galactic center, and I had to map it and take images. This was at a time when there weren't many images, and it was in the infrared. But even in a 30-second exposure, the images were confusion limited. There was a star per pixel, and
Wow.
you can't see the fainter ones when the brighter ones already fill up each pixel. And it turns out for the early universe images, like in the paper, Rayhan, that you saw, it probably has images in it. It's not confusion limited, so it isn't quite a galaxy per pixel, but there are a lot of
Right.
galaxies.
How would you do
Mm.
any type of analysis with a galaxy or a star per pixel, for example?
So you would measure the light from each star uh, down to the point in brightness where the
Mm.
stars merge. So you can imagine, let's say there's a star per pixel, um, but if you cut off the brightness at a certain bright level, you only see a star per every 10 pixels
Oh, right.
Okay.
because there aren't as many bright ones, and then there are a lot of medium brightness ones, and then a ton of faint ones. So the confusion limit means that you can't see fainter than a certain brightness.
Hmm. So it's kind of just like a minimum level that anything below it just looks like noise. But if
Yeah,
you were to subtract it, then
yeah,
the signal from anything brighter would remain,
yeah,
and then all of that would just go to zero.
yeah. So if you think, imagine that you want to measure the amount of light from a bright star. And so what you could do in your software in your computer is you can uh, get the signal for every pixel, let's say in a 3 by 3 grid of pixels centered on the star, add all those numbers up, and at this point you can say, wait a second, you're also getting light from all the faint stars that are unresolved. They're inseparable. They just create a blur. So what you then do is take a piece of the image next door where there's no bright star, but just the faint blur, and then measure all those
Mm.
signals, and you subtract the two, and you're left with just the light from the bright star. And then you can relate that to the absolute amount of energy emitted by the star through a calibration.
Mm.
Okay.
I
You've
want to
been
go back
mentioning.
to.
Go for
Go
it.
ahead, Ray.
Oh no. Okay. I would just. You were mentioning using imaging the galaxy cluster way back when you were doing your thesis and whatnot. And I'm assuming you're still using infrared detectors. I know on your website you're trying to make a new class of infrared
Yeah,
detectors and whatnot. So I guess my question is, how does new technology get incorporated into these detectors? As in, would you say that it's mainly like software improvements that have carried over the years? Have there ever been like some major advancement in like CCD technology that's been like, oh, we need to put this in all of our detectors now? Or
yeah,
has it been more gradual? Or what does the technological advancement look like in such a field?
yep. I don't. So just starting out with software versus hardware, I don't think there's been much advancement in the software.
Okay. Oh,
Um,
oh, really? Oh,
yeah, I
I
mean,
would think it was the.
so
I guess I
we
see.
use different languages. So when I started out in junior high, I guess uh, I learned basic
Oh,
and
nice.
and you know basic, right? And then in high school I learned assembler code.
Wait, you learn assembler code?
Yeah, machine.
That's
Yeah.
wow.
Oh,
That's very intensive.
well, it was called macro assembler, but it was
Okay.
it was in uh, human readable form. It wasn't zeros and ones, but it was one level above assembler or machine code. And so you would write. So what you were doing is you were commanding instructions
Right.
in the command set of the CPU, and also manipulating numbers and registers.
Right. No,
And then
I've looked at assembly code before. It looks devastating. I don't
yeah,
know how anybody can write like that.
yeah. So then after that, I remember I was in college and I wanted to work for a professor in high energy physics at Fermilab,
Hmm.
and he said, "Do you know Fortran?" And I said, "Pretty much." And he said, "Well, have you taken a class in it?" And I said, "No." And he said, "Well, you have to go home this summer and take a class, and then when you come back, show me your grade, and then I'll hire you." So I went home, went to the community college, which is a fantastic community college. I went there during high school too. And I went to the computer instructor and I said, "I want to take your Fortran class, but I'm not gonna go to your class. I'm
Okay.
just gonna I'm just gonna hand in the homeworks and do the exams." And he said, "Fine." So I did that. I got an A. I think I got a perfect score, like 100 or something. So I
Nice.
went back to the
Wow.
professor and I said, "Here's my
Nice.
grade." And he said, "Fine, you can work." So that's Fortran, and then C, and then in astronomy they created these data processing environments. So one of them was called IRAF, which was
Okay.
I think it was image or interactive reduction for astronomy facility. I probably got every single one of those words wrong. I don't remember, but it was an environment where like a classical environment, you type the name of the executable at the command line, and then it puts you in the environment, and it has a
Okay.
different prompt,
Okay.
right? Kind of like a
Yeah.
Oh, okay.
Python or something, right?
Right. Right.
And then you're typing commands away, and there are ways to create programs that you could run the programs, and it was both an executable and an interpretive environment, so you could type and get immediate response or run whole programs. Okay, and that was written by University of Arizona uh, funded by NSF, and everyone used it. And then there was APES, which was the image reduction facility for Chandra, or AIPS. Um, Actually, I can't remember if it was Chandra or radio telescopes, but it turns out that different wavebands invented their own environments, software environments, because the techniques were somewhat different. And then after that, there was an environment called IDL, which was interactive
Mm.
data language, I guess, that was written by just a small group of people, and their company's been bought and sold 10 times over or something. And I think L3 Harris across the street from me owns it now. And so then people in astronomy, they converted all the IRAF libraries over into IDL. Okay. And then came along Python, and many people switched over to that. But my point is, I've programmed in most of these, but not all. But I could program in all of them because to me, they're all the same. You just look up different commands or whatever. And for the most part, the sophisticated aspects of those programs are not used in astronomy.
Mm.
Whatever fancy object oriented or God knows what fads there are these days, they're generally not used. And to me, Python looks the same as any other language. It looks like Fortran.
Oh, what? Oh, I'm gonna clip that.
So, the question is, do you put a semicolon here? Do you put a colon, or do you put an equals, or is it a double equals? You got to go look at a help
Yeah.
page or something. But
Right.
Right.
but they're all the same. Uh, the fact that you can do interpretive work in Python, that's the same as most of these. Also, the fact that you can use a notebook like in a browser, like to me that's not profound. That isn't any different than anything else. So they're all similar to me. I don't think there's been much progress in the software. Everything runs faster, but I,
Right.
I
Right.
but I
Which
think
is what
that's
I
the
would imagine.
CPU. I started
Right.
out. I had one of the first computers in my city. I couldn't afford an
Wow.
IBM, so I got a Canadian company to build a computer for me, but I wanted it to be compatible, so they smuggled in a Chinese copy of an IBM ROM, and then
That's
Wow.
and then we had to pay off someone at the border so that they wouldn't inspect it.
what? That's
And then
hilarious.
you had the first computer in your city.
Yeah, yeah. Well, the
That's
first
a
like
that's a
IBM
notable
computer,
feat.
it was. But my point was going to be that it was blazing fast, 4.88 megahertz.
Wow. Blazing
Wow.
fast.
Yeah,
That's a not even a fraction of what we get
yeah,
these days. That's
yeah,
crazy.
yeah,
Yeah. Wow. So
yeah.
software has definitely advanced a lot. I mean,
It,
sorry, in terms of
Hardware,
speed, but
hardware.
not in terms of
yeah,
the actual what you're doing, just in terms of speed.
yeah.
It's been
Now I have no doubt that there's software that would blow my mind, like some machine learning AI type thing. Maybe I don't know. But my point is astronomy is basically just brute force software. I think that the interesting thing about the software in astronomy is maybe the data processing algorithms, like to synthesize data from a radio array, is
Hmm.
pretty damn cool. But that's not a
hmm
that's not innovation of the software. That's just you just implement the algorithm. The innovation's in the algorithm, which can be
right,
written
right,
written
right.
down on a piece of paper. So on the hardware end, it's been completely different. In fact, you could ask a slightly different question: what fraction of Nobel prizes in astronomy or related fields is almost solely due to technology? And it's either all or most, unless you go back
Wow.
100
Really?
years. Yeah, 100
Wow.
years, you could get a Nobel Prize for thinking.
Hmm. Right.
Those are more sparse these days.
Right,
Yeah,
but
quite.
but but these days, you get a Nobel Prize if you use a telescope that's bigger than the previous one and you shoot fish in a bucket.
Hmm.
Yeah.
Right? So if you look at the Nobel Prizes like the Accelerating Universe, that's highly attributable to sensitive CCDs, which is a technological innovation that was made in the late 60s, early 70s. Um, and the guys who did it went to their boss at Bell Labs and said, "Here, we're working on this thing called bubble memory, where you have PN junctions that can store charge. turns out it's sensitive to light. We might be able to make this into some sort of detector, and then people eventually could talk to each other while looking at each other on a phone. And then,
I
and
mean,
then their
were they
bosses,
thinking that at the time?
yeah, yeah, and then their bosses
Wow.
said, "We haven't heard anything crazier. That's the stupidest idea we've ever heard," and they killed the project.
Wow.
Now, it was early
Wow.
though, right? So maybe
Yeah.
that's a good business decision. Similar thing happened to one of the big companies you might have heard of that made film. It was called Kodak,
Mhm.
and their engineers came to them and
Right, of
said, "Look,
course.
we could use these CCDs and we can make cameras." And their boss said, "Shh, don't tell anyone about CCDs. We have a film business." So they're down the street in
So,
a big empty building now.
no.
Yeah.
So
So what would they
what has
use? What would like
CCDs?
astronomers use
Oh,
before? Oh,
sorry. I think no. I think my
sorry.
Wi-Fi
There's
just
an
conked off,
internet
so I didn't
problem
hear what
here.
you said. Go for it.
I was asking what were astronomers using before CCDs?
That was literally my question.
Take a
Fantastic.
guess.
Their eyes. I don't
Almost
know.
between the eyes for a while, and then eventually CCDs. But in the interim 100 years, it was film.
Okay.
Mm.
And the best film, the most sensitive. When I was a kid, I used to order this sensitive film. It was from Kodak, and it was called 103 AF or 103 AG. I forget the names. And I used to get it hypersensitized with hydrogen gas. So if you took the film and you put it in a bath of hydrogen, and then you get the company to put it in a cold pack and send it to the mailing you, and then as soon as you get it, you put it in the freezer, and then you take it out and put it in your camera and on your telescope in your backyard.
Mm-hmm.
And the clearest nights were in the winter when the moisture was frozen out, and I would be sitting there with my eyebrow frozen on my little eyepiece with the reticle with my little clock drive, my drive corrector, and I had one of these old-fashioned hair blowers that you'd see in these salons. A bunch of women in the salon have these big hair blowers, and it has a big tube on it. And I would stick the tube with the hair blower that blew hot air. I'd stick it pointed at the corrector plate in the front of the telescope that sometimes would get moisture on it, condensing on it. And then every once in a while, I'd
Mm-hmm.
flip it on and it would go shh, and it would all go away. And then at the other time, I'd take it and I'd stick it up my leg in my ski pants because it was so cold out. So I'd go between being warm and frozen and then having the front corrector plate being clear or fogged out by the humidity. But I used to use that film and it was more like twice the sensitivity as the non-gas hypersensitized film. And astronomers would use that film uh, often on glass plates. So instead of flimsy film, it would be a glass plate, and Kodak would make these, and they would deposit their emulsion on the glass plate,
Oh.
and the astronomer would put that in a camera. And there are places that have old observatories, especially that have these vaults full of glass plates. And there was a big effort in the 80s and 90s. I think it was the 80s more so to digitize these glass plates by having a little scanner with a camera in it, and it would scan across the glass plate and then record the brightness so you'd be able to see the stars and galaxies. And that's a database now that you can use, and it's called the Digitized Sky Survey.
Oh, cool.
So
Oh.
if you've ever gone to Simbad or there are a bunch of other ones that people use or mast. You can
Mm.
choose to see any field based on coordinates with this digitized sky survey. So it gives you a picture of what that piece of sky looks like, and that's the digitized photographic plates that were used. And CCDs are about 50 to 100 times more sensitive.
Wow. So the observations immediately got way, way better.
Right. So now your question, Rayon, was where are the innovations, software or hardware? And so I've now given two examples. I explained the software, And I just
Mm-hmm.
explained eyeballs to film to CCDs. And
Right.
each of these led to a revolution of discoveries, right? So again, if you plot the discoveries and um, plot the Nobel Prizes, uh, it isn't like humans are getting smarter. It's the hardware that's doing it. And in fact, I gave an example in the lecture I gave. Parker, I don't know if this came across because I had too many slides, but I wanted to give the example of the Nobel Prize for the discovery of the supermassive black hole in the galactic center. And it's something I had worked on. And so it turns out you can infer the presence of a massive object if other things orbit it.
Mm-hmm.
So you can know that the sun exists or has a certain mass if you look at the fact that the planets orbit around the sun. And even if someone blocked you from seeing the sun, you would know that the sun's there because of their orbits, right? And so there was a project initiated by Reinhard Genzel to look at stars in the galactic center and look at their velocities, both their motions in the sky, but also their Doppler shifts, and then calculate their orbits, and then infer the mass of
Of
a
what they're orbiting.
yeah, of what they're orbiting. And for as soon as people invented infrared detectors, they saw things moving at a high velocity around the center of the galaxy. So there again, infrared detectors immediately led to the knowledge that there's something very massive. They didn't know if it was all in one object or dispersed. And so Reinhard Genzel created this project to measure stars as close as possible into the center in order to confine the possible volume in which this mass could be distributed. And eventually get to the point where you have to say, you know what, that's got to be a black hole.
Mm.
And
So,
and
what are the challenges that exist in trying to image the center of
right,
the
right. So,
galaxy?
so one thing I already told you was the dust. The dust means you can only do the infrared. The infrared means you need infrared detectors. Infrared detectors had to be invented.
Mm-hmm.
And so that started in the late 60s when Gary Neugebauer and Eric Becklin, one of my thesis advisors, used lead sulfide military detectors uh, comprised of a single pixel. Their camera had
Wow.
one pixel, and they took images by moving it.
Wow.
Oh wow. Oh
You know,
wow.
it's like people say, well, back in my
Interesting.
day, I had to walk uphill both ways to and from school in 10 feet of snow, right? Well, he used to tell me about his one pixel when he was my thesis advisor. So he discovered the galactic center, uh, and eventually um, other people like Judy Pfeiffer and Bill Forrest across town at University of Rochester from me, and George Reiki and Marsha Reiki, they started to use a new kind of detector, which instead of having one pixel, had 58 by 62 pixels. So that's better,
Mm-hmm.
right? And if you put it under a microscope and look closely, right on the border, you can see a little cartoon of a tank and then a missile coming into the tank. Those were the tank killer devices that the military
Wow.
developed. And so I came along at the time when it was 128 by 128. This is in like 1990, 91. And then I went to 256 by 256, then K by K. JWST has 2K by 2K, and the W first or Roman telescope has, I think, 4Ks. Um,
Wow.
so
So, is it a running theme that military innovation leads to innovation in the detector world?
yeah, yeah, I think so. There's a little bit that goes the other way too, and
Okay.
I don't know if I don't know how much that is. My guess is it's far more the other way from military to science. So, and you asked about that because I talked about the detectors, but let's talk about another innovation, which is um, adaptive optics. So this is where you can change the surfaces of optics in a system.
Mm-hmm.
And
That's actually what I'm doing my master's in.
okay, so
Or,
you can
yeah.
correct the optics for various aberrations, or it could be externally induced aberrations along the line of sight, say from the sloshing effects of the atmosphere. So the atmosphere is inducing differential wavefront error across the field. And this makes that beautiful airy pattern that made that sort of Gaussian shape I described earlier, it blurs it way out by like a factor of 10.
Mm-hmm.
Okay. Um, the military was developing that. And I don't know if I said this in the lecture, but one of the programs they were developing it for was this thing called Star Wars. And it's not the movie. This was this thing in the 80s where they spent tens of billions of dollars to develop the technology, and astronomers eventually got a hold of it. We're very sneaky. Like the first tank killer detector, from what I understand, was Alan Hoffman worked at Raytheon, and he was sort of a frustrated astronomer. And so I've heard various versions of this story, so I won't say the details. The net result was Judy Pfeiffer ended up with a tank killer device in her desk at University of Rochester, and I think Alan was her former student or something.
Mm.
So infrared detectors, adaptive optics. Now that little airy function, when you use adaptive optics, you can get rid of all the blurring, and the images for point-like objects go back down to that airy function. The bigger the telescope, the smaller the airy function. So the better and better and better resolution. So the third innovation was big telescopes. And there was a big competition in astronomy for like 50 years as to whether big telescopes should be made with single big mirrors, or that's Roger Angel down at University of Arizona. He makes these big mirrors. Or if big telescopes should be made with small mirrors that are cobbled together and segmented to mimic a big mirror. Kind of like a radio telescope array, except they're all adjacent and they're hexagonal so that the gaps are minimized. The question was, which one would win? And this is all documented in a book called Big Telescopes. It's a fascinating book. So it turns out they both won because they were both competing for the national telescope. And the argument was the nation could only afford one big telescope and they would have to choose. When I say they both won, I'm lying a little bit because the big telescope is called Gemini and it uses monolithic mirrors. And that's the national funded telescope. So technically, Roger Angel won. Except there are private telescopes that prefer the segmented mirrors, right? Like Keck. So Keck has segmented mirrors. So anyway, segmented mirrors you had to have to do this project.
So why did you have to have segmented mirrors?
Roger Angel doesn't make mirrors bigger than 8 meters, and so
Oh,
maybe I shouldn't say that because let me finish the story about Reinhard Genzel. I
sure,
said
sure.
he made up this project, right? What I wanted to say after that is there's another group that uh, uh, did the same thing. So they heard about what the German group was doing, Reinhard Genzel, and they copied it on Keck. So Reinhard was using the European Southern Observatory, ESO, the very large telescopes, because in astronomy we have awesome names for telescopes, and those ones are very large. And so, but those are all 8 meters. So I was incorrect when I said you had to have segmented mirrors. I should have said that these segmented mirrors and the big monolithic mirrors represent big mirrors, big telescopes, infrared detectors, adaptive optics, big telescopes. And those are the three reasons why the Nobel Prize was given to Reinhard Genzel and the American group 400 years after Kepler and Newton wrote down the equations that they used.
Wow.
Okay? Because Kepler and Newton could have got the Nobel Prize if someone had given them infrared detectors, adaptive optics, and big telescopes. So how much
So
is big science and discoveries and Nobel Prizes dependent on technology? It's 99%.
right. So the
Wow.
knowledge was always there.
Oh yeah,
It
yeah.
was just actually applying it.
I've explained this to my 8-year-old.
Yeah. So I guess the way to speed run a Nobel Prize is definitely go into the technological side.
Yeah, I don't know. I mean, it's the number of people who have a Nobel Prize is a very small number.
Yeah.
So maybe your odds go from 0.001 to 0.002 or something percent. I don't know.
Yeah.
Doesn't seem like a winning. I guess the idea is going for a Nobel Prize is kind of a hard thing to do.
Yeah.
I was wondering about in general just new telescopes. So when you say, like, for example, I'll give you the easiest example that maybe you can talk about, James Webb versus Hubble. When you say we're making another telescope or making a new telescope, you've already explained that hardware has advanced a lot. So is it that you make, like, what is it that you're really focusing on? Or I guess it might also be project specific, but in general, when you're making a new telescope, or for example, as I was mentioning, you have a new infrared detectors in your next year's goals. So my question is, what do you do when you make a new telescope? What are you focusing on? Are you focusing on bigger mirrors, as you mentioned, better CCDs? What are you focusing on in particular? Or, and this easiest example you can talk about is James Webb versus Hubble, for example.
Yeah, so I started working on James Webb Space Telescope in 1999. I was the detector scientist for several years before I left that job and came to RIT. So I saw the development of the telescope up until
Right.
the up until the point that the technology was frozen.
Oh,
As soon as the technology was frozen, I quit.
wait,
Uh,
technology
be,
was frozen as in, like, it
yeah,
didn't,
the design. So
like,
James
it
Webb Space
plateaued.
Telescope is flying technology that was state of the art in 2006. It's obsolete.
Mm,
Wow.
damn.
Except for the fact, well, the technology is obsolete. The telescope is cutting edge.
Hmm.
Okay,
So,
because there is no telescope that's better because it takes 20 years to develop a telescope.
Right. So, what were they like focusing on in that
Right,
development of that new
right,
telescope? Like, just
right.
in
And
general.
and, but, and by the way, I'm working on the one that's going to fly in 20 years. Okay, so
what?
working
What?
on it then, I was involved in that process, and here's the way it went, and this is generically true. Someone decided that they wanted to answer a scientific question, and it needs to be big enough to motivate a very expensive new instrument. And so the question wasn't even a precise question. It was more like we are going to explore the cosmic web of matter in the early universe, which in itself has a bunch of sub questions that really do have question marks after them. Like, when did galaxies form? How did galaxies assemble? How did galaxy clusters assemble? What were the first stars like? Were they different than stars now? So you can imagine writing all these down.
Right.
Then you could call that your level 0 requirement. And then for a level 1 requirement, you might say, for each question, I'm going to write down the capabilities that my system should have. So to look at these things, we need a spectrograph. To look at this thing, we need an imager. To look at this thing, we need to have very long exposures. To look at this thing, we need very short exposures because they're transient events. So you write all this down, and those are your level 1 requirements. And then your level 2 requirements might be this imager needs to be take images at these wavelengths with this spatial resolution with an optical system that has a certain magnification. Uh, it should have a certain sensitivity, and et cetera. And that's level 2 requirements, let's say. And then level 3 would say, given the level 2 requirements, this imager has to have this kind of detector.
Mm-hmm.
And the detector has to have a certain quantum efficiency, dark current, and read noise, and et cetera. And you can imagine doing this process and creating a tree, sort of. And in the end, you end up at the bottom, which God knows what that is, but I've seen spreadsheets full of this crap and really make your eyes gloss over. At the bottom, it says, I'm going to use a 440 screw in each slot, right? There's actually a document on fasteners on screws at NASA. Okay,
Wow.
Oh,
so
I could see that.
yeah, well, you have to, right, or
Yeah.
things blow up, right? And you have to use the right units. So ultimately, this process is the recipe for building a system and James Webb Space Telescope was no exception. The one somewhat remarkable thing about it is a number of technologies had to be invented in order to satisfy the requirements. And that's bad because that represents what NASA calls risk.
Hmm.
And one way to do risk mitigation, especially if you can't fix it when it's on orbit, is to pay a bunch of money in development and testing.
Hmm.
So JWST was heavily tested, and that's one reason why it cost so much. It was 10 billion, and we originally told Congress 600 million.
Wow, a little over, just a tad bit.
Yeah, over budget.
Yeah,
But that's, I'm
I read a
assuming,
book
pretty
about
normal.
how big projects will never ever follow the correct timeline or the budget. So
Yeah,
I could have predicted that one.
it's really strange because in some ways, um, you want to present it to Congress as if it's like building a highway road, which people have done a million times with a lot of certainty. Uh, but that's actually not what it is. It's much more uncertain and difficult and innovative. So it's a delicate balance how to sell projects to the government without getting in trouble.
Further questioning that level 2 requirement that you were mentioning, I'm just curious on, so would it mean that JWST, for example, can only do like a certain range of experiments? Because what if one day someone was like, oh, this is obviously the best telescope that we have in our use in terms of like spatial measurements, I'm assuming, and oh, I needed that filter, but shoot, it isn't on there. Like, is there
Yeah,
anything like that that happens, or?
yeah. Another way to think about that is, let me phrase your question differently. How many fist fights in back alleys were there amongst astronomers competing to make JWST do different science or do their science
Mm,
in
Yeah,
the early days? And there
right.
were all sorts of fist fights. And one of them, I think was resolved well. Was should we use gold coating on the mirrors? And if you've seen the telescope, you know the answer is yes,
Was that
we
for
did.
heat purposes?
No, so this is what I'm going to explain. So gold is more reflective at long wavelengths than silver, but it has a really sharp cutoff at around 600 nanometers and below, and that's right in the middle of the optical.
Oh,
mm,
So there were people left out in the cold, all the UV astronomers, of course.
yeah.
Of course, you can just tell the UV astronomers you can do UV astronomy, just redshift it
hmm, hmm,
if you look at the early universe, right?
Yeah.
Um, but people, I'll say we, had to keep telling the UV and optical astronomers that this isn't your telescope. You'll need a different one. You have Hubble, and this is an infrared telescope because a level zero requirement said, you know, investigating or deconstructing the cosmic web in the early universe. So you see how this little pyramid tree is important
right, right, right.
Hmm.
when people come back and they say, "You bastard, why did you cut me out?" And then you say, "Here's the tree," and the star at the top says it's going to be an infrared telescope because of the science.
Mm.
Okay.
So is the reason why you left the project because everything that had to be done on the detector side was finished in 2006, and so
It was a combination of things. I wanted to leave Space Telescope Science Institute, which is where I was at. That's where the project was developed. Uh, One of the places, and NASA too. I left that place because that place, it's difficult to do hardware at that place, and I was doing instrumentation development. It was set up to do more like image analysis because it's the place that operates the Hubble. And when you have a Hubble, you don't have to build it; it's there, and so they take data. Uh, that's one reason why I left. Then I went to RIT because that was the best. I felt that was the best place to go for a variety of reasons, but partially because of the instrumentation. And in some sense, you're right that whether I stay there or not, I would have stopped instrumentation development for JWST at that time because it was already done.
Hmm.
There was nothing to do. At some point, once the innovation is done, everything gets handed over to engineers who, you know, make drawings and then build it.
Right. So then it became an issue of actually getting it in space and having it stay there safely.
Yeah, yeah, and that was, a lot of us were surprised when it worked. I was having a dinner with the head of NASA one day, um, who had been visiting my lab earlier in the day, and he asked me if JWST was going to work, and I said, "Well, I'm not on that project, so
No comment.
that's the nicest thing I could say."
What were your doubts about it?
Oh, I don't know, everything. There was something like 170 or something critical point failures or something, single point failures on it, where if that one thing failed, the whole mission would fail. And that's the largest of any NASA mission ever. So I guess any of those 170 things, like the solar shades wouldn't
Mm-hmm.
unravel properly, or something would
Right.
go
I
wrong
was
with
I
the
was hearing that.
deployment. Remember, I had to deploy,
Right.
Yeah.
so
Right.
that whole procedure. Um, there are many steps in that procedure. Maybe you remember data coming out every week or two, where you'd see another image and it would look better and better and better. Eventually, the final images came out. They're beautiful.
Hmm.
Mm-hmm.
That was an exciting time. I remember.
Yeah, yeah. I was showing my class every time a new picture would come out. I'd say, look at this, awesome. Yeah,
So I mean, luckily it
Yeah.
didn't check it. I mean, so far at least, I think none of those flags have been hit. Right, like everything went successfully.
yeah.
For you,
I think
or
so. I heard of a glitch related to the mid-infrared imager MIRI, the MIRI instrument. I'm not sure
oh,
whatever happened. I think it got fixed, but
what do you do with
yeah.
like how do you fix something like that? Is it just software? I mean, I'm assuming you can't really do anything with the hardware.
I'm not sure. Well, given the fact that I can't remember exactly what the problem was with
Right.
that, I
Right.
can't say
Mm.
in that case. But in some cases, for instance, with a detector, there can be certain effects that can be annealed out, is what they call it. It's where you heat it up and then cool it back down, and
Mm-hmm.
it pushes some of the atoms around,
Mm-hmm.
and corrects certain effects like dark current.
Okay.
So that's an operational thing. Another thing
Right.
was, I think, Hubble's in low Earth orbit, so it's zipping around the Earth once every 90 minutes. And there's a high radiation place called the South Atlantic Anomaly, or the SAA, and you can choose to orient your instrument packages in a certain way to minimize the cross section between the
Mm-hmm.
high energy radiation and the detectors or electronics. In some cases, you want to close your lens cap when the telescope is sweeping near the sun. That's an example. So Chandra had a problem with that at one point. Um, so they had to change the operations. So my point in answering your question is, it's possible through a change in operations to mitigate the effects,
Okay.
these effects. Because for
Right.
JWST, you can't go there.
Mm-hmm. Right. Right. That's. I mean, even with Hubble, I mean, I don't think anybody ever physically gone to fix Hubble because it's much
Yeah,
closer.
yeah, they had SMB, service. Uh, I forget what it stands for, but it's servicing mission. Yeah, servicing mission. So there was servicing mission, I think 1, 2, 3, 4A, and 4B. So that might be five. Oh, the head of NASA, the guy I was telling you about that I was having dinner, he flew on one. He
Oh.
flew on one of these missions to fix Hubble. Yeah.
Wow.
Oh, is he an astronaut of any sort, or is he just
Yeah.
the head of
Yeah, he's
NASA
an
that wanted
astronaut.
to go? Oh, okay, okay, that makes
He
sense.
yeah.
Okay,
No, he became the head of NASA later, and NASA
okay,
has some tradition of their head administrators being astronauts. Not always, but they did do that.
Oh, fascinating.
Cool.
Fascinating.
Yeah.
So, just to like continue on the JWST, I know you very briefly glossed over something that I would like to talk about, where you said I'm on the project that's going to be released in 20 years. My
Oh,
question
yeah.
is, my question is, I mean, number one, if you would like to share what that project is, and number two, I mean, actually, let me just ask you that question first, because I think the second one is a little break off
Yeah.
of the first one.
So remember I was telling you about the street fights in the alleys?
Right, right.
Okay, that's where we are now.
Okay, okay,
So so,
okay. Still
so
figuring out what to do.
yeah, so
Hmm.
there's this thing called the decadal survey, which is done every 10 years, as the name suggests, and
Right.
it's where the community comes together and then they write down what we should all do for the next 10 years. And then that's a document that is used to tell NASA and the National Science Foundation what to fund.
Right.
Okay, and in the last decadal survey, um, there were all sorts of competing ideas considered, and the authors recommended a um, Frankenstein-like combination of two concepts. So there were a bunch of people who wanted the habitable uh, exoplanet uh, telescope, HABEX, and then a bunch of other people wanted the LUVOIR, which is the large UV optical infrared telescope. I was the co-chair of the technology working group for LUVOIR, so NASA asked me to lead that to determine what detectors need to be developed,
Oh wow.
which is part of my philosophy. Is we use instruments today that have obsolete technology to understand what to develop in the future, and
Hmm.
then we become part of the future projects. And when those future projects publish reports about what's needed, we're the ones who are authors, and then we write proposals to build that technology that we recommended that NASA fund.
So this new technology, is it? I'm a little perplexed because or like just curious, I guess, because you mentioned after the invention of CCD, it just changed everything. So now, are you just what? Are you just packing more pixels into it, and is that new technology, or are you like making different like new camera technology every decade or so?
Yeah, I
And
would
if it
just
is, what does it
answer.
look like?
I would answer generically, sort of.
Okay.
So it's a bit subjective, isn't it? I mean, if you have a 1K by 1K detector and then you replicate it, but in a format that's 2K by 2K, then you could say, okay, fine, it's new technology, but it's kind of not. It's just bigger. But someone could argue, yeah, but that bigger meant that you need bigger growth foundries, which are expensive, and you had to solve geometry problems by having a bigger detector. There are geometry problems without me going into it. So 0 to 10, I don't know, maybe it's a 3 in terms of
Hmm.
new technology ness, you know. But what we're trying to do is develop single photon counting detectors, which I think are much closer to a 10 on a
Hmm.
on a scale for new technology, and then implement them in gigapixel per detector format. And right now, the biggest in astronomy is 16 megapixel.
Okay.
So this LUVOIR wants to have a gigapixel focal plane, which I mean, I was on the project, so we had anticipated would be composed of hundreds of detectors butted together.
Okay.
And so what I want to do now is replace all that with a single chip that's a gigapixel.
Hmm.
And it's single photon counting, which is what you need to detect biosignatures or life on another planet. You need single photon detectors.
On your website, it's mentioned for next year's goals to develop single photon detectors for quantum applications. And I was simply
Yeah,
wondering, in addition to these bio, how do these technologies help things like quantum imaging? And what really is
yeah.
quantum imaging?
Well, so let me tell you about an experiment that a colleague of mine is doing in the Center for Detectors, Professor Greg Howland. So imagine a crystal that can spontaneously convert a single photon into two entangled photons. So spontaneous parametric down conversion, SPDC. And imagine pumping it with a laser of photons that all have the same energy, and some fraction of them are converted into two photons whose total energy sum up to the energy of the original photon. But they're entangled and they conserve momentum, and they'll propagate outward from the crystal at an angle with respect to the optical axis. So they'll kind of make a triangle. And the further away that they propagate, the farther apart they are from each other because they're propagating out at an angle, right? Like that. Now they're going to strike a detector. If you put a detector in the way, they're going to strike the detector at the same time. So the problem is, to do this experiment, you want to have single photon counting detectors so you don't lose one, right?
Mm-hmm.
And up until recently, the only single photon detectors available were sort of made with one pixel. So like a photomultiplier tube or a avalanche photodiode type detector. So the way they did this experiment was they put the one pixel in one place and they generated the two photons. And then if a photon hit the pixel, they would record that. And then they would move the pixel again and repeat it. So this is back to trying to map the galactic center like my thesis advisor did by using a single pixel. And then at the very end, but you know, in this single pixel version of the experiment, you can never detect the two photons at the same time,
Mm-hmm.
right? So you could only use statistics to see where the photons landed after adding all the events up to know if your experiment was truly creating entangled photons, because the illumination pattern will look a certain way if it's these
Mm.
entangled photons. It's in the statistics. So a better way to do this is to take an imaging detector and replace it, instead of having the single pixel, replace the single pixel with an imaging detector with lots of pixels. Then you can get events at the same time. And that's what Greg Howland's trying to do. And this is a quantum entanglement. It's called quantum entanglement verification.
Oh,
Oh. Right.
verifying
So
quantum
so it's
entanglement
not
with
it's
imaging.
not when you say quantum imaging, it's not that the detector itself is taking advantage of the properties of quantum mechanics. It's that it's taking observations to kind of perform quantum mechanical experiments.
Yep. Yep. And
Oh,
I
okay.
think that's often the case. Um, when you see quantum experiments in general, the detectors are like these click detectors. They're called, where you get a click if a photon hits it. But the quantum experiment is an optical effect, and the quantum mechanics happens between the emission and the detector. It's usually not the
Right.
detector that's leveraging some quantum effect. Now, to some extent, what I said is wrong in the sense that people often talk about quantum 1.0 and quantum 2.0. Okay, and 2.0 means leveraging entanglement, leveraging indeterminate states and entanglement. Okay, quantum 1.0, the detectors actually do use quantum 1.0, and everyone uses quantum 1.0 every day in a nearly infinite number of ways, because quantum 1.0 enables uh, things like circuits and p-n junctions. The concept of a band gap and energy levels in an atom is a discretization of a
Right.
continuum that wasn't recognized before quantum 1.0. So quantum 1.0 was 100 years ago, right? When Schrodinger
Right.
and Bohr and all those people wrote down the original rules of quantum mechanics, and the immediate implication was that the energy levels are discretized, or they're quantized,
Mm-hmm.
which is what
Right.
quantum means. Quantum 2.0 that you've heard about, all this new stuff with quantum, has to do with leveraging entanglement and indeterminate states where, um, the state of a photon is not known until it's observed or recorded. And you can take advantage of the indeterminate state, um, for instance, to do computations and exercise in parallel many computations at the same time because of the indeterminate states. But by the way, there's a neat book called Q is for Quantum, and it's by Terry Rudolph, who unfortunately doesn't have his grandfather's last name. His grandfather was Schrodinger.
Oh wow.
Oh, that's quite unfortunate.
Or maybe it is fortunate. I don't know. What goes over better at a cocktail party? Is it Rudolph or Schrodinger?
Well, I would.
Depends on what party you're going to, right?
Right.
Exactly.
Definitely depends.
So,
So,
are there any talks within the detector community of kind of replacing the PN junction with some kind of quantum 2.0 version of it?
I don't know about that. There's one application for quantum astronomy that's being developed in Australia at the University of Sydney, and I haven't looked into it enough to really comment on it, but I think it's similar to the synthesizing signals from an array of telescopes like they do in radio.
Right.
mm-hmm.
Yeah. I mean, it's the talk of the town right now is quantum computers and how that's going to revolutionize uh, the the world of computing. And so, I thought maybe there would be some analogous kind of discoveries happening in um, other aspects of technology.
Well, there's uh, yeah, there are other technologies that leverage quantum 2.0 that aren't computing. Uh, have to do with sensing and pointing and navigation, measuring small changes in the gravitational field due to the presence of a submarine nearby.
Oh my
You can
god.
imagine certain
Oh,
people might want to do that.
That's
wow.
like trying to calculate the force of gravity of attraction between two people, you know.
Yeah, or two metal spheres, right? Isn't that what Cavendish did?
Henry
I'm
Cavill.
not
I
familiar.
forget.
Yeah, I think
Why?
that's what he
Why?
did.
Why? Why would you do something like that though? Is radar
Well,
not sufficient enough, or is it just
imagine
like a proof of
uh,
concept?
imagine you want to find a sub. Now, you might not want to find a sub, but you can imagine, I bet, some people who do want to find a sub, right? And
Okay.
imagine one way to do it is you emit a sound wave and then measure
Mm-hmm.
if a reflection comes back. And this is called sonar. One of
Right.
the problems is the sub can pick up that sound wave. Sounds like a ping. And
Mm-hmm.
now they know you're looking for them. And now they just detected you. So you were trying to find them, and the first thing you did was indicate to them that you're there. So instead, imagine that you wanted to measure the slight change in the gravitational field due to the mass of the sub. And it's a tiny, tiny change. But if you did that through some sensitive instrument that could precisely measure time uh, and the perturbation of the instrument due to the extra gravity, you could do that in a stealth way,
Mm-hmm.
right? They wouldn't know that you're doing it.
very sensitive equipment, I'm assuming, would be required for said calculation.
Yeah. So it
Like
leverages.
extremely sensitive.
Yeah, it
How
leverages.
would this leverage quantum? How would this
It
leverage quantum?
leverages quantum 2.0. I can't remember the details of it, but it almost always has something to do with the precise manipulation of atoms, um,
Right.
kind of like an atomic clock uh,
Right.
measuring
Actually,
the frequency.
I just remember what you were talking about, the Cavendish experiment with the attraction between two spheres and measuring kind of the torque
I
by
think
one
so.
another.
Yeah. I think that's what
Yeah,
Henry
yeah, yeah,
Cavendish, wasn't it?
yeah.
Wasn't it one of the options to do for our experimental,
Yeah, I
or
think
am I?
actually,
I think
yeah,
it was right.
at U of T, the undergrad physics labs, that was kind of an experiment that you could conduct yourself, um, for as part of one of the experiments on the list that you could pick from. So, I think that's where I remember it from actually. But yeah, very interesting stuff. Um, yeah, I mean,
Yeah.
podcast has been going on for
I
about two
I
hours.
just want to know one last thing. I just want to know
Yeah.
one
Sure.
last thing. Maybe I think this is like the perfect way to segue to a close. Where do you think the future of detectors are going? Do you think something like I know you very briefly mentioned artificial intelligence, machine learning. I know these are all buzzwords, but do you actually think that they could maybe have some kind of play in the future of detectors, maybe the design of them? Do you see new technology and maybe, as you mentioned, quantum 3.0 maybe actually being somehow implemented in detector technology? Basically, where do you see the future of this field going?
Yeah. I think the easiest answer is that uh, they're going to be perfect, and then I'll have nothing to do. I'm trying to time this with when I retire.
Okay,
Because like,
nice,
right?
nice,
I think I
nice.
think you want to make yourself
That's a smart
obsolete when you
idea for
retire.
sure.
Yeah. Um, the quantum efficiencies are nearly 100%. The read noise is nearly zero now with these single photon detectors. The dark current is essentially zero now. The signal that the detector generates itself, we've gotten rid of that.
Wow.
Um,
Okay.
so many characteristics are so good now that I think it's essentially going to spell the end to detector development eventually. Except what often happens is we have this need to always create something better or to figure out how to do things that our technology can't do. So we have to invent new technology like JWST.
Mm-hmm.
So
Mm-hmm.
there's a funny thing in astronomy, and I think it's true of all science and maybe all of humanity. Once you could do something, it's not as interesting.
Yeah,
That's nice.
yeah,
That's nice.
It's more
True.
it's more
The chase is more interesting.
yeah. I think there are analogies with dating for some people, right? So so I guess that's embedded in humanity. I don't know, but so as soon as they become perfect, someone's going to come along. Like I've had people call me to develop detectors to look at the sun. And I say, why do you need better detectors to look at the sun? You need more sensitive detectors. And what they said was, well, they have so much light, they decided to make a super high resolution spectrograph that splits the light in wavelength to very high resolution. So you're taking all the light and splitting it. And then they decided to split it in polarization. Then they decided to take microsecond images. So basically, they changed the application until the problem was the detector guy. So
Mm,
they drove the application until they didn't have enough light, and then they
right.
started crying that they didn't have enough light and the detector needs to be better.
Right.
right.
Right. Right.
Right. So I think they're becoming essentially perfect, and then people will invent new applications that have never been done before, and then that's going to require something else, I guess. I don't know what that is.
Mm-hmm. So you would maybe say, in your personal opinion, that or it's more camera technology has more or less plateaued. Would you say that?
Um, the detectors, I think, are nearly perfect for many astronomy applications, and then the
Mm-hmm.
camera is usually the part, like the lenses and everything else, in addition to the detector. And um, yeah, there are innovations in optics too that are still
Mm-hmm.
continuing.
Mm-hmm.
Hmm.
Okay.
Well,
Well,
awesome.
I
This was
think that was
a An
That was a lot
awesome
of
conversation.
yeah. That I personally have learned a lot more about how cameras and cameras in general work, because I think that was also a main goal for us to get. I mean, detectors are obviously very relevant in terms of astronomical applications, but in terms of day-to-day lives, as you mentioned on the phone, the millions of PN junctions that I now know I have on my phone.
Yeah,
So,
yeah. Have fun with
I,
your PN junctions.
right, right.
If you ever get lonely, remember you have millions of them. Oh, there's one other thing I wanted to mention, which is something fun. Recently, I was asked to review something, and it involved the Unruh effect,
Mm-hmm.
UNRUH, and that's one of three guys in the 70s who basically predicted the same effect. I'm not an expert, and I don't understand it that well, but it's crazy, and it involves a detector. So imagine you had a detector, and it is, let's say, looking at nothing, empty space. Well, that's a trick. That's a trick phrase, empty space, because space isn't empty even when nothing is there that we can see. Supposedly, it's full of vacuum fields that can be energized into higher level states to create particles. So particles are just vibrations of these vacuum fields. So here's the
Right.
fun part. Imagine you took the detector and you put a rocket behind it and you sped it up at very high acceleration. Due to relativistic effects, it will see particles from the vibrating fields in the rest frame.
Hmm.
It'll see particles in its frame of reference.
Right.
Wow.
Someone looking at the vacuum fields will see nothing.
Yeah. Not enough energy.
Yeah. So I thought that was really cool, and I think it's related to Hawking radiation, which is a GR effect near the event horizon.
Would this not simply be just related to the pair creation and annihilation of particles, like these virtual particles that are appearing, or are you not?
I,
Are you talking
I
about
think
something more
so. I just
specific?
I think
Right.
so. Like I was saying, I don't know enough about this except to know that this is a
Hmm.
really cool application that I had never thought about that involves
Yeah.
this
No,
detector.
that is really cool, actually. Like,
And
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 anytime I
in
hear
fact,
about something,
what they did
sorry,
was
go ahead.
they calculated the photons that the detector would see as a result of this, and it turns out to be a black body, and the temperature is 10 to the minus 21 Kelvin times the acceleration. So if you want to figure out how to detect this to win a Nobel Prize, then you need to get the acceleration really high, and then you could see this black body maybe 1 Kelvin if you're lucky.
Wow.
And this would be the black body distribution of these energy fields that are present in a vacuum.
I guess so. And the main I think the main point of people who think about this is it's a probe of those vacuum fields because those vacuum fields are otherwise not observable. We take it with a
Right.
matter of faith that particles are instantiations of higher energy modes of these vacuum fields, right? We
Mm-hmm.
say that the vacuum fields exist. And so this was going to be another detection of it or measurement of it, more
Right.
direct, or maybe you could detect other characteristics of the field doing this versus doing something else.
Mm-hmm.
Hmm. This
Yeah,
reminds
because
me
I
of
guess we've
like
yeah.
taking an image of a black hole, right? It's
Mm-hmm.
something that people
Yeah, yeah,
suspected was there, and then once the technology advanced to the point where we could actually take a picture of it, it's like, okay, now we have an actual image of it. So
Wow.
now it's kind of the same thing, but with these
yeah,
invisible
yeah.
fields.
Wow.
Yeah.
Okay, well maybe that'll. I hope you don't wake up with nightmares about the Unruh radiation
The
effect.
under
Yeah.
Detectors accelerating at you real fast tonight.
That's definitely something that'll keep me up. I feel like it's definitely quite an interesting effect because I mean, who thinks of imaging empty space? But now here we are.
Yeah,
So I
well,
feel like
you can bring this up at your next cocktail party, and we'll see
I
if
will.
it clears a room or brings everyone into the room.
Yeah.
Depends on the party.
Depends on the party. Definitely depends on the party.
Yeah.
Well,
Yep.
I must say thank you so much for coming on the podcast, coming on the show.
Sure.
Um,
Thank you guys. Yeah.
It's been
All right.
lovely to have you here, a lovely conversation, and I think we've all learned a lot. Hopefully our viewers have as well. And actually, I must say, just before adding this on, just like a little extra tidbit here for people that listen to us but don't like follow our Discord and whatnot. We actually mentioned that we were recording an episode with you on the Discord before we actually had this, and we got a bunch of questions from other people as well that we did incorporate into the
cool.
into it. So I'm just saying, for future listeners, if you want to get to know the next guest or maybe have some questions and you want us to ask them, join our Discord. Link in the description. So yeah, just like another extra little tidbit for you guys there.
Awesome. Yeah. So yeah, for anybody who's listening right now, make sure to follow us wherever you're listening to this podcast. And I hope you enjoyed it. Have a good day, and we will see you next time. This is the Math and Physics Podcast.
Bye.
I'm your host, Parker.
And I'm Ray, and we will see you soon. See ya.
Bye, guys.